Hello everyone and welcome back to episode 4 of the mini video tutorial series on computational models. In episode 3 we concluded by suggesting that there exists an alternative format for signed integers referred to as 2's complement format, as mentioned in the concluding remarks of episode 3. We will reserve the discussion for why we choose to implement 2's complement format over 1's complement format on the modern day CPU chip for later. Let us first strengthen our understanding of power series relative to the discussion at hand, before we explore the more delicate intricacies or deep mathematical questions relating to 2's complement and computation. We first restrict our attention to understand how 2's complement format encoding works. So to understand how 2's complement format works, we will first require a basic understanding of the following mathematical fact about power series, and in particular, power series of base 2. Note the emphasis on the word series, which just means to add up a bunch of terms of a sequence. We thus have the following lemma. Given any integer b greater than 1, and finite exponent n, then the sum of all lower powers up to and including the second last term is always less than the highest power. This can be more easily expressed as a relation involving base b and exponent n indexed 0 through n. It is symbolically b to the power of n is greater than b to the power of all the reducing exponents, all the way recursively down to 0. From the above lemma, we obtain a corollary if we set the base b of the power series to 2. In the following example, we demonstrate the above lemma and corollary by comparing the highest power on the left-hand side of the inequality to the sum of the lower powers on the right-hand side to show that this inequality is true for this particular case. From the above discussion, it should be evident that if we subtract the left-hand side from the right-hand side, then the resulting integer sum will be negative, since a smaller number minus a larger number gives us a negative number. In contrast to the case number 2, that if we subtract the right-hand side from the left-hand side, then the resulting integer sum will be positive, since a greater number minus a smaller number gives us a positive number. Before moving on to 2's complement and discuss how this fact relates to it, let us prove this fact first to gain confidence in our claim that this is actually true for any number b greater than 1. Since if it fails to be true, we are not permitted to use it for constructing the 2's complement format number universe. We will prove that this is true using a direct proof scheme or heuristic. We proceed as follows. Suppose that b is greater than 1. We claim that b to the power of n is greater than the sum of all the reducing powers of n. To prove this claim, notice that if b is greater than 1, then it should also be that b minus 1 is still greater than 1, because b is greater than 1, and b is an integer. Also note that b to the power of any number n is greater than b to the same power minus 1 for any b greater than 1 and any positive integer. So surely, dividing the right hand side by b minus 1, which is greater than 1, we get that b to the n is greater than b to the n minus 1, which is also greater than b to the n minus 1 divided by b minus 1, since the larger denominator produces a smaller quotient. Note that the right-hand side, b to the n minus 1 over b minus 1, is exactly the nth partial sum of the geometric series starting at b to the n minus 1 all the way down in reducing powers up to b to the 0. Thus, we have proved the claim that for any b greater than 1, the largest power is greater than the sum of all the lower powers. It is, of course, an immediate consequence of the previous theorem that if b is 2, then the rule holds. We are interested in this particular case for the context of the discussion, since for any n-bit word, we are dealing specifically with power series of base 2. Let us revisit the example of the 4-bit all ones binary numbers 1111. Notice that the leading bit or most significant bit is 1 at index 3, thus evaluating to 8, while the sum of the lower powers evaluates to 7. By the above proof, we are guaranteed that the left-hand side will be greater than the right-hand side. Now we are ready to discuss 2's complement while keeping in mind the above fact that we have just proven. So a binary number, say x, in 2's complement format encoding maps a given sequence of 1s and 0s to signed integer numbers according to the rule, which may seem very confusing at first, but which is in fact equivalent to the previous theorem, just written in a summation notation to capture the observation that subtracting the highest power of 2 from the lower exponents always produces or maps to a negative number, while not subtracting the highest power of 2 at all, in other words its coefficient is 0, reverses the situation, instead maps to a positive integer. Let's do 2 more examples to obtain a clearer understanding of 2's complement format encoding. Example 1. Calculate the signed integer value using 2's complement for the binary number 0101. To evaluate the binary number in integer format, we start with the second highest power of 2, fill in the appropriate coefficients all the way down, then subtract the highest power of 2, which in this case has coefficient 0, thus subtracting nothing. Example 2. Calculate the signed integer value using 2's complement for the binary number 1011. Then of course the result is obtained in a similar way as before by starting with the second highest power of 2, fill in the appropriate coefficients all the way down, then subtract the highest power of 2, which in this case has most significant bit equals to 1, thus subtracting a larger number, resulting in a negative 5. Let us now focus our attention to talk more about the all ones and all zeros to complement binary encoding. Clearly, the 2's complement of the all zeros binary encoding is attained if all the coefficients of power series base 2 is 0. In contrast to 1's complement encoding, the 2's complement of the all ones binary number is mapped to negative 1. In other words, if all the coefficients x subscript I is 1 for all indices I ranging from 0 to the last index n minus 1. Finally, let us investigate the 2's complement range by determining the two extremes endpoints, in other words the maximum or minimum of an n-bit binary number in 2's complement format. The minimum integer value that can be represented by the 2's complement format is ascertained by the appropriate choice of the base 2 power series coefficients as follows. Let the most significant bit be 1 and all the lower powers of 2 have coefficients 0. In summation notation, this looks as follows, which evaluates to the formula negative 2 to the power of n minus 1 for the minimum integer representation in 2's complement format. The maximum integer value that can be represented by the 2's complement format is ascertained by the appropriate choice of the base 2 power series coefficients as follows. Let the most significant bit be 0 and all the lower powers of 2 to have coefficients 1. This evaluates to the highest possible number since all the lower powers of 2 contribute to increasing the sum, while not subtracting the highest power of 2 from the result, since its coefficient is 0, thus resulting in the maximum possible value that can be represented using only n bits. Thus, the range of the 2 complements number format is from negative 2 to the power of n minus 1 up to 2 to the power of n minus 1 minus 1. Notice that the range of 2's complement format is skew in the sense that there is one extra negative number in comparison to 1's complement format, which gives us a completely symmetric interval. So this makes us wonder, why would 2's complement be a better choice to model negative numbers over 1's complement? Well, as discussed in episode 3, we want to preserve unique inversion between the number and its representation. In other words, there is a one-to-one correspondence between 2's complement encoding and the number that they represent in its range. Let's depict this visually by drawing a relation diagram for a 3-bit 2's complement encoding. Unlike with 1's complement encoding, 0 does not have a unique representation, whereas 2's complement encoding preserves the one-to-one and surjective map. Thus, this map is a bijection, which preserves and guarantees a unique inverse for each element. Furthermore, it gives us that the 2's complement map and unsigned integer map are econumerous in the sense that they have the same finite number of elements. Thus, we can use the same number of bits to represent unsigned integers as well as signed integers. This brings us to the conclusion of episode 4. In episode 5, we will start to explore binary fractions and investigate the IEEE 754 standard for encoding decimal fractions in dot notation or in mantissa format, using floating point and double data types to approximate recurring fractions as well as the real number system for precision in calculations to achieve a higher degree of accuracy.